and welcome to the next in our series of PYB 350 overview videos. Last week we looked at the omnibus one-way ANOVA and found that we could tell that there was a significant difference between our means somewhere. This week we're going to look at how we can follow up on our one-way ANOVA to find out exactly where that difference lies. So let's carry on with the example that we had in our last video, where we were looking at the effects of sleep deprivation and caffeine on a neurological test of temporal memory. So our IV was the experimental condition. Yes, you either had no sleep deprivation and caffeine, no sleep deprivation and a placebo that didn't contain caffeine, 36 hours of sleep deprivation and caffeine, or 36 hours of sleep deprivation and a placebo not containing caffeine. And our DV was a recency discrimination accuracy score. And this is what our data looked like. Yeah, our grand mean was 14. We had 7 people in each cell, giving us a total N of 28. And A is the number of conditions in our experiment. In this case, we had 1, 2, 3, 4. So our SPSS output, when we conducted a one-way ANOVA, showed us that we had a significant difference between those 4 conditions somewhere. Yeah, here's our ANOVA summary table. Yes, our sums of square between, our sums of square within, and our F statistic of 25, which is significant, telling us that there's a difference between the mean of those 4 conditions. We just don't know where exactly it is. So we need to conduct follow-up tests to see what conditions the differences in recency discrimination lie. So these tests can either be post hoc, yeah, so if we have no specific hypotheses about where the differences might be, we look at the differences between all possible means, so all possible post hoc comparisons. Or they can be planned. So if we have specific hypotheses or specific contrasts of interest that we've decided upon a priori, that is, before we conducted the experiment, we can run a series of planned comparisons to test those specific hypotheses. So, for example, suppose the researchers designed this experiment to test the following specific predictions. A, that sleep deprivation will result in a decrease in performance on the recency task. And B, that caffeine consumption will improve performance on the recency task. So we could carry out 2 planned, complex, because they'd be involving more than 2 groups, comparisons to test these specific hypotheses. Okay. The difference between post hoc and planned comparisons is all about how we control our type 1 error rate. So remember, every time we make a comparison or conduct a statistical test, we have an alpha % chance of making a type 1 error. Yes? So in our case, where we set it at 0.05, we have a 5% chance of making a type 1 error. Experiment-wise is the total chance of making a type 1 error across our whole experiment. Yes? So that is our alpha level multiplied by the number of comparisons that we run in our experiment. However, what we're most interested in, is our family-wise error rate. That is the probability that one or more comparisons will result in a type 1 error rate in following up a particular effect. Okay, so in the case of a one-way ANOVA, experiment-wise and family-wise error are actually exactly the same thing because we're only following up one effect. When we move into two-way designs, we'll see that the family-wise error only relates to a single IV, whereas experiment-wise error will relate to the number of IVs that we have in our whole experiment. So now, you would think it's very easy. Why don't we just control for all the comparisons that we have to do, divide it by 0.05 by all the comparisons that we have to do. But what happens there? The lower we make our alpha level, the harder it is to get a significant difference. So there's always this trade-off between type 1 and type 2 errors. Making a mistake and saying there's a significant difference when there's not one, versus not picking up a significant difference when it is actually there. So we need to choose the most appropriate technique for controlling our type 1 error, while balancing that out against the chance of making a type 2 error. So there are a number of techniques that statisticians have devised for controlling this type 1 error rate across multiple comparisons that we need to make in a complete experiment. In choosing the most appropriate technique, the main consideration is whether we are making a few carefully chosen comparisons that are planned a priori to running the experiment, or whether we've chosen to look at all possible comparisons in a post hoc way. Now, the important thing to note is that none of these change the way that the F statistic for the comparison is calculated. What they all do is adjust that F critical value to which our F obtained is compared. Also, as they're pairwise comparisons, any of these can also be bootstrapped. So, for our a priori comparisons, the most common technique we have for adjusting for type 1 error rate is simply a Bonferroni adjustment, which simply means the number of comparisons, or dividing 0.05 by the number of comparisons we need to make to keep our overall type 1 error rate for all the comparisons at 0.05. In our post hoc space, there's lots of options that we have depending on whether our assumption of homogeneity has been breached or not. However, the most common post hoc procedure is Tukey's. So, let's have a look in more detail now. For planned comparisons, they can actually be carried out with or without a significant overall F, but it's still quite common to run your omnibus ANOVA first and then the planned comparisons to test your specific hypothesis. Keppel and Wickens actually suggest if the number of planned comparisons doesn't exceed our degrees of freedom between, then we don't need to make any adjustment at all. However, the most common procedure that we do see applied to planned comparisons is what's known as the Bonferroni adjustment. So if your number of planned comparisons exceeds the degrees of freedom between, or degrees of freedom effect, we Bonferroni adjust for the set of planned comparisons we need simply by dividing the 0.05 error rate by the number of comparisons. So for example, if we have 3 comparisons that we need to run to test our full set of hypotheses, 0.05 divided by 3. So our new significance level, rather than being 0.05, is 0.0167 for each of our planned comparisons. If it was 4 comparisons, we divide 0.05 by 4, coming up with an alpha level of 0.0125 for each comparison. In terms of effect sizes, we can easily use Cohen's d as the most appropriate measure of effect size for a pairwise comparison. We just use MS within from our omnibus S test as our S pooled. So we just look at the difference between the two means that we are comparing and divide it by the square root of MS within to gain our Cohen's d. Right, so how do we run our planned comparisons in SPSS? So pairwise comparisons among all means are available in either the EM means options menu in GLM or our post hoc menu in GLM and in OneWay. So SPSS will provide Bonferroni adjustments for our pairwise comparisons, but note that these adjustments will be applied for all possible pairwise comparisons. So if you have just a specific number of planned comparisons that you want to look at, what's best to do is just to apply no adjustment, or LSD, choose the LSD option, and then apply your own Bonferroni adjustment yourself. For complex comparisons, it's a little trickier. In one way, it's very easy. We've got that lovely little contrasts option box, and we can assign the weights for the comparisons that we want. In GLM, it's a little bit more complex, and we actually have to go into the syntax and add a special contrast command. So let's have a look first at our one-way and looking at how we might do complex or pairwise comparisons, specific ones, using the contrasts menu. So let's have a look at the two contrasts that we want to run. First, that sleep deprivation will result in decreased performance. And second, caffeine consumption will result in increased performance. So you can see there what we're actually interested in is the groups who were not exposed to sleep deprivation versus the groups that, or the conditions that were exposed to sleep deprivation. So to test that contrast, we'd simply assign the same weights to the two control conditions and contrast them by assigning the same and opposite weights to the sleep deprivation condition. Remember, your contrasts, when you add them all up, they must always add up to 0. Okay, our second contrast is looking at comparing caffeine versus our placebo group. So again, we compare the two groups, assign the same weight to the two groups who are given caffeine, and contrast those by assigning the same and contrasting weights to the two placebo groups. Okay, then SPSS will simply tell us this was contrast 1 and it was significant, this was contrast 2 and it was not significant. So these contrasts are telling us that sleep deprivation had an impact on performance, but caffeine consumption did not. So just a couple of things to keep in mind. To test our two predictions, we needed two complex comparisons. Yeah? They were complex because they involved more than two means. They were a combination of groups. That's what a complex comparison is. We did this by assigning the appropriate weights to the treatment means through the contrast menu. So effectively, each of these tests is what's called a single degrees of freedom test, effectively a t-test. But there's a couple of key differences I want you to be aware of between t-tests and the contrast that we conduct here. The main difference is in the contrasts here, we're using the pooled variance estimate, our MS within, from the overall ANOVA, rather than just the variance associated with the groups that we're contrasting. The other thing we need to remember is because we're now conducting multiple tests, we may need to control that alpha level. Yes, that depends, as we looked before, on the number of comparisons that you're making and whether they're planned or post hoc. So remember, there's always that trade-off between type 1 and type 2 errors. So the more we control our type 1 error, the greater our type 2 error is. And so therefore, the lower our power, the less likelihood we are of picking up an effect if it's there. So just remember that trade-off and to always tell your reader when you're reporting what adjustment you have made for those comparisons. Okay, in GLM, there's no nice contrast box, but the EM means menu does give us a way to get those planned pairwise comparisons. So you just simply select the effect you're interested in this case group, move it into the display means box and require it to compare the effects. Yeah? That's what generates the pairwise comparisons. Now here is where you can specify either no adjustment or a Bonferroni adjustment or a CDAC adjustment. Remember, if you're doing plan comparisons, it's probably best to leave it at an LSD, which is no adjustment, and then apply your own Bonferroni adjustment if needed. If you apply the Bonferroni adjustment here, it will adjust for all possible pairwise comparisons. And this is what your output looks like. Yeah? This is the comparisons for the control, the group who were not exposed to sleep deprivation but received caffeine, compared to those who were not exposed to sleep deprivation but received a placebo, and we can see there was no difference between those groups. However, there was a significant difference between the two groups that were exposed to sleep deprivation. And here are our confidence intervals for the difference. Remember, this is not the confidence intervals around the mean of these conditions, but the confidence intervals around the mean difference between these groups. So complex plan comparisons in GLM is not so great. There is some pre-packaged contrasts that you can choose from. But the easiest way, I think, is just to go into the syntax and specify your own complex contrast. So that way you know exactly what you're asking for. So we already worked out the weights we needed for our two complex contrasts to look at the difference between those exposed to sleep deprivation and those not, and those who received caffeine or those who received the placebo, which is simply when we're running our ANOVA in GLM, we click on paste and that will take us into the syntax menu. And then we simply add this line here. So we want to get a contrast of the IV group. Yep. And it's a special contrast, and this is exactly what we want. Okay. And it will bring up your contrast output looking something like this. Here's contrast 1 and here's contrast 2. So you need to know what contrast you've asked for so you know what this output is referring to. So again, we can see there was a significant difference, yes, between those who were exposed to sleep deprivation and those that weren't, but no significant difference between those who received caffeine and those who received the placebo. So remember here, you need to apply your own Bonferroni adjustment. So in this example, we've got two contrasts, so we could assess our significance level at 0.05 divided by 2. So that would be, it would be significant if it's less than 0.025. Or we could simply cite Keppel and state that no adjustment was made because the number of comparisons was less than the degrees of freedom effect, which in this case there were 4 groups, minus 1 equals 3. But just let your reader know when you're reporting your results what you actually did. So post hoc tests. Post hoc tests are nice and easy to run in both one way and GLM. Field recommends that if you have not breached your homogeneity of variance assumption, to use a Tukey's if you've got equal ends. But if you've got very unequal ends in your groups, he recommends using Hotchkiss. If you have unequal variances, so your homogeneity assumption has been breached, he recommends using Games-Howell. In most cases, the test that you actually choose will make very little difference to your actual results. But again, what's important is to specify clearly what kind of post hoc adjustment you've used and the rationale for it. So the post hoc menus in one way in GLM look exactly the same, and running a Tukey's or a Games-Howell is as simple as ticking this box or ticking that box. And our output, regardless of which box we tick, will look exactly the same. It is just the adjustment to our significance levels that has been applied will differ slightly whether we use Tukey's, Games-Howell or another test. So again, we read this simply as here, this is the post hoc comparisons between those people who were in the condition where they did not or they weren't exposed to sleep deprivation and they received caffeine versus those who did not or were not exposed to sleep deprivation and received a placebo. No significant difference there, but there is a significant difference to the two groups that were exposed to sleep deprivation. That output will also pop up a little thing here that's called homogeneous subsets, and it's very easy to read. Anything that's on the same column does not differ significantly from each other, and anything that's on the opposite column does. So here we can see the two sleep deprivation conditions do not differ from each other, but the two of them do differ from the two control conditions. Okay, to run bootstrapping, very simple. Remember, our omnibus ANOVA is not bootstrapped, but any of our planned or post hoc comparisons can be bootstrapped. We can do that in either one way or GLM. And bootstrapping is good to use if you do have a small sample size or you have minor breaches of your assumptions, just to increase the confidence in your results. So our ANOVA output looks exactly the same, but what happens here is that we get bootstrapped results for our contrasts. And as we can see, while we're getting the same pattern of results, the bootstrap significance levels are slightly different from the levels that we have by running our contrasts straightforwardly with our full samples. Yeah. Remember, because bootstrapping is resampling every time, so every time you run it, these will be slightly different. Okay, in GLM, our ANOVA, exactly the same. And our post hoc comparisons, okay, give us our bootstrapped significance levels, and it gives us our bootstrapped confidence intervals for the difference between those two conditions. So, in terms of our research question, what have we found? So, one-way independent groups ANOVA showed that the experimental condition did have a significant impact on recency discrimination scores. And there is our F-test from our omnibus ANOVA. And in this case, I'll report the planned complex contrasts to test the hypotheses of the effect of caffeine and the effect of sleep deprivation showed us that recency discrimination was significantly affected by sleep deprivation. And that is the results of our complex comparison comparing the sleep-deprived conditions to the not sleep-deprived conditions, but not by caffeine. And this is the contrast where we compared the groups who received caffeine with the groups who received the placebo. Remember, if you're writing up a full result section, you'd add means in there, confidence intervals, effect sizes, and talk about the adjustment that you made for those follow-up tests to control for your family-wise error.